Hello student, this is the part of lecture number 9, and today we are going to understand the theories of failure. Theories of failure is very important topic of machine design because it helps to find out the dimensions of the component. Means any component we are going to design, the dimensions of that component can be calculated on the basis of theories of failure. Actually, in any design condition, we consider the different types of loading. Means your component is going to be subjected with different types of loading, and at same time and simultaneously it may be subjected to different types of loading. And due to this complex loading system, there may be a complex stress generation, and your component will be subjected to a complex stress system. And at that situation, how your component is going to be failed, that is more important. And this point of failure should be predict very precisely and accurately, so that you can be able to find out the dimensions on that particular point of failure. And for calculating this, the exact point of failure, or to relate the point of failure with the dimensions of the component, there is a bridge which is known as theories of failure. So theory of failure works as a bridge, or it works as a tool which enables you to find out the dimension of the component under very complex situation. And it also by relating the material properties with the complex loading system. So in that way it helps you to find out the dimension of the component. So let's see how theories of failure will help you to find out the dimension, and also how many types of theory of failure are generally used to predict the dimension in case of ductile or brittle material and under static and dynamic loading. In real situation, there are number of machine components which are subjected to several types of loading simultaneously. When the component is subjected to several types of loads, combined stresses are induced. For example, in case of a shaft which is on which at one end there is a pulley, or there is a flywheel which is rotating, and there is a pulley which with the help of belt it is rotating. Then at that situation, torsional moment induces torsional shear stress, while bending moment causes bending stress in the transmission shaft. So at the same time, there are two types of stresses are generated in the shaft, which combinedly make a complex system of stresses. Theory of elastic failure provide a relationship between strength of machine component subjected to complex state of stresses with the mechanical properties obtained in tension test. Actually, the properties which we get is calculated on the basis of tension test, as we all are aware about the universal testing machines, where we get proportional limit and ultimate strength, yield strength, fracture point, and all these properties. On the basis of that, we actually, and at this situation we all know there is a uniaxial loading. So the properties which has been calculated or determined, that is based on the uniaxial loading. In actual conditions there may be biaxial or triaxial loading system, or it may be more complex system. So at this situation your properties should be related to the, I think very precisely and accurately are related to the, I think point of failure or under stresses under with the combined stresses. Means property should be directly or indirectly, or there may be some method to relate properties of the material to the combined stresses, so that the dimensions of the component can be calculated. So in these situations these theories of failure will help you. With the help of these theories, the data obtained in tension test can be used to determine the dimension of the component. Same thing I have discussed with you, irrespective of the nature of stresses induced in the component due to the complex loading. Means that in real situation there is a complex loading system, but under these complex loading, with the help of theories of failure, students can be able to find out the dimensions of the component. Means property that you know can be related with the complex stress system to find out the dimensions with the help of theories of failure. That is the main, I think, essence of this theories of failure. Failure of such components grouped into categories. These two categories are static failure and static failure theories for ductile material, static failure theories for brittle material. Means I think this is grouping for your easiness, and there is two category of material, one is ductile and other is brittle. And for these two types of material the theories of failure are also different. So let's see first the different types of static failure theory for ductile material. To find the safe dimensions, two cases will be considered. In any case or in any theories of failure there may be two conditions. One is when SYT is equal to SYC. SYT is yield strength in tension and SYC is yield strength in compression. This is first case. Then for ductile material, maximum shear stress theory and maximum distortion energy theory may be used, and in later slides we will discuss about this. May be used to find the dimension of the component. So in the first case, when SYC is equal to SYT, then maximum shear stress theory and maximum distortion energy theory can be used to find the material dimensions of the ductile material. And in the second case, when SYT does not equal to SYC, means yield strength in tension and yield strength in compressions are different, then Coulomb-Mohr theory can be used to find the said dimensions. But at UG level, in many cases you will see that SYT will be SYC, and if it is not given in questions then the first case will be considered. So be careful while you solve the question. I think you should pay attention on these facts. In the next case you will study the maximum shear stress theory, and the short form of MSST I think it is known as MSST, and it is full form is maximum shear stress theory. Maximum shear stress theory this is I think reduced or aggregated by C.A. Coulomb, H. Tereska and Guest. These are the scientists which have developed this theory of failure or criteria of failure. The theory states that failure of a mechanical component subjected to biaxial or triaxial stresses occurs when the maximum shear stress at any point in the component become equal to the maximum shear stress in the standard specimen of tension test when yielding starts. As the name suggests, I think you should pay attention on title of this theory. Maximum shear stress theory means maximum shear stress will be the criteria to decide the failure, and your component will be failed when it is subjected to triaxial or biaxial loading system and it reaches to the maximum shear stress of the standard specimen of that material. Means whatever loading system is acting on the component, we have to calculate the maximum shear stress which is being induced in the component, and that should not be beyond, or it should not be exceeds from the maximum shear stress of material which determined on a standard specimen in the tension test. In tension test, specimens subjected to uniaxial loading, as we know, as I have already discussed at UTM, you will see there is a uniaxial loading. So sigma 2 will be 0. Obviously, there is only one direction of force, so one stress will be induced. At that situation, maximum shear stress will be equal to sigma 1 by 2. And when specimen start yielding, means when specimen start yielding, then at that situation the stress will be equal to the strength of the material in tension, the yield strength of the material in tension. So when specimen start yielding, then we can write sigma 1 is equal to SYT, means sigma 1 will be equal to SYT. At that moment material will start yielding. So in the first, I think in this equation we can put in the place of sigma 1 SYT. So in this way we will have a result that will be used in many cases. When we will design something on the basis of maximum shear stress theory, then maximum shear stress can be calculated with the help of this formula. What this formula or this relation tells you, that maximum shear stress theory predicts that yield strength in the shear is half of the yield strength in tension, that is SYS is equal to 0.5 of SYT. Actually, in simple tension test we don't know, or we do not calculate or determine the shear strength of the material. So with the help of this theory we can have a relationship with shear strength of material to the yield strength in tension, means shear strength in tension means yield strength in shear, that is SYS is yield strength in shear is equal to half of the yield strength in tension. So this is very important formula, and in many cases when we will calculate the dimension of the component, then we need to calculate this one too. So need to remember, and very important formula. Suppose components subjected to sigma 1, sigma 2 and sigma 3 are the three principal stresses at a point on the component, then according to MSST, maximum shear stress theory, tau max can be calculated by this means which any one, sigma 1 minus sigma 2 upon 2, or sigma 2 minus sigma 3 upon 2, sigma 3 minus sigma 1 should be less than or equal to SYS upon FOS or SYT upon 2 FOS. FOS is factor of safety. The SYS, yield strength in shear, yielding in yield strength in shear upon FOS, but we have already, I think, determined SYS is equal to 0.5 of SYT. So put these value and you will get the same relationship. So in this equations we can have, if we know the principal stress working on a component, then we can directly calculate the sigma max, and that sigma max, tau max can be can be equated to the shear strength, yield strength in shear or yield strength in tension to calculate the dimension of the component. Tau max means maximum shear stress can also be calculated with the help of Mohr circle, per radius of Mohr circle, that can also be utilized to find out the value of maximum shear stress. The above relationships are used to determine the dimension of the component. Means these are the relations with the help of you can calculate the dimension of the component, which is going to design on the basis of maximum shear stress theory. With the help of maximum stress theory in a complex system, we can have, or we can draw a region under which region, or under which under the boundary of that region your component may be safe. I think there would be a I think combination of the stresses that will tell you about the situation where your component may be safe, or beyond that boundary your component may be fail. So in case we are taking here biaxial stresses, so sigma 3 will be 0, and MSST equation can be written as sigma 1 minus sigma 2 is equal to this first equation, sigma 2 is equal to plus minus SYT is equation number second, sigma 1 is equal to plus minus SYT is equation number 3. There are the three systems when we consider biaxial system. Now plot these equation on XY axis, and what we get, we will get a equation, a line CD, which is based on the sigma 1 minus sigma 2 is equal to minus SYT, and the second line is this in positive side, sigma 1 minus sigma 2 is equal to plus SYT. Similarly, sigma 2 and sigma 1, with the help of sigma 1 and sigma 2 we can have these two lines, and when we see, or when we look with the help of these line equations, now we have an enclosed area. This is the I think area where we can see at any point different types of combination of stress, sigma 1 and sigma 2. Means at any point we can have two values of sigma 1 and sigma 2 in this region. So what maximum here shear stress theory tells you, that if your component is subjected to a biaxial system of loading, where at any point the combination of sigma 1 and sigma 2 is under these boundary, then means what it tells, the combination of sigma 1 and sigma 2, if at any point of situation or any point of loading, if it is the combination of sigma 1 and sigma 2 is within this region, then your component will be safe. And when these combination exceeds this boundary, then your component will fail. So by making this diagram, or by knowing the reason of safety, a designer will have some situational data or some operational data within which we can run our component, or we can use this data to find out the dimension of the component. This is the basis. Based on the above equation, reason of safety can be constructed, which is in the figure. I think we have already calculated. The maximum shear stress theory of failure is widely used by designer for predicting the failure of components which are made of ductile material like transmission shaft. So this theory is mainly used in case of ductile material, and it is a conservative theory to predict the dimension of the component, because it generally considers as a safer side to calculate the dimension of the component which is made by ductile material. Let's see another theory of failure for ductile material, which is very widely used, maximum distortion energy theory, MDET. In short form we can say. This theory was advanced by M.T. Hoover in Poland 1904, and independently by R. von Mises in January 1913 and H. Henke in 1925. Generally von Mises are very popular, and the stress which will be we will calculate will be known as von Mises stresses. So mainly credited to von Mises to introduce this theory of failure. The theory states that the failure of mechanical components subjected to biaxial or triaxial stresses occurs when the strain energy of distortion per unit volume at any point of component become equal to the strain energy of the distortion per unit volume in the standard specimen of the tension test when yielding starts. So again, the language of theory is very similar to the previous one. The only difference is that here we are considering strain energy of distortion per unit volume at any point, and that should not be exceeds the strain energy of distortion per unit volume of standard specimen of same material in tension test. So in this way we can understand this, and if for calculating on the basis for calculating the strain energy per unit volume, here in case of principal stresses MDET, von Mises stress can be calculated. So von Mises stress can be calculated with the help of this formula, and that should not be I think that should be less than or equal to SYT upon FOS. That is the limiting. SYT is the material strength in tension, and FOS is factor of safety. So in any case, von Mises stress should not be greater than the SYT upon FOS, otherwise your component may fail. And how we can calculate the von Mises stress? With the help of this formula we can directly calculate the value of von Mises if we know the value of principal stress like sigma 1, sigma 2 and sigma 3. In case of simple stress, means if we know sigma x, sigma y and sigma z, then we can also calculate the value of von Mises directly by putting the values in the given equation, and that should also should be less than the SYT upon FOS. In case of 2D stresses, sigma 3, sigma x or sigma z or sigma 3 will be 0, and the equation will be reduced in this, and again we can have this equation. This bone mysis stresses should not be greater than SYT upon FOS, and this, with the help of this relation, we can directly calculate the value of dimensions of the component. According to the distortion energy theory, the yield strength in the shear is 0.577 times the yield strength in tension. That is very important result, and you need to remember, and you have to pay attention on this. What you see there here, yield strength in shear is now 0.577 times the yield strength in tension. What you see as compared to previous one, here your shear strength is increased now. Means in earlier case we have seen yield strength in shear was 0.5 of SYT, but here you will see, and you are seeing shear strength is 0.577 of yield strength in tension SYT. So this is the very important, I think, prediction, and with the help of this we can, I think, we can take more aggressive design compared to previous one. Aggressive means the dimensions of the component will be less as compared to previous one. Means if you are following MSST, maximum shear stress theory, then dimensions will be larger as compared to the MDET. So that should be kept in your mind. Region of safety. If we draw the region of safety for the biaxial stresses, then we can see in earlier case the equation of bone mysis stress with SYT is a equation of ellipse. So by using the ellipse equation, we can draw a ellipse on the stress system, two-dimensional stress system, and from this you can understand if at any point within this region of safety the combination of sigma 1 sigma 2 will be safe at any point in this region, but beyond this line of ellipse or boundary of ellipse, if the combination exceeds or combination goes out from this boundary of ellipse, then your component will be failed. So this is the prediction, and when you compare with the previous one, you will see it is more aggressive than the maximum shear stress theory, and it predicts better and precise than the maximum shear stress theory. So for a designer, if you want to take conservative side, then you should go for the maximum shear stress theory, and if you want to be an aggressive designing, then you should choose this one. But in many experiments it has been proved that this predicts better I think failure of material under different types of loading. Experiments have shown that distortion energy theory is better agreement for predicting the failure of ductile component than any other theory of failure. Now we are moving to the material brittle. We have already seen two theories of failure, maximum shear stress theory and maximum distortion energy theory. These two theories are generally used for ductile material, and in the next I think case of brittle material, we'll see the maximum principal stress theory, and most widely used theory for predicting dimension of the component which are made by brittle material. The criteria of failure is aggregated by British engineers W.J.M. Rankine, so sometimes it is known as Rankine Theory 2. The theory states that the failure of the mechanical component subjected to biaxial or triaxial stresses occurs when the maximum principal stress reaches the yield or ultimate strength of the material. So language is again very similar to the previous theories of failure. Here what you see, any material will fail which is a biaxial or triaxial system of loading or system of stresses when the maximum principal stresses reaches the yield strength of the or ultimate strength of the material. So in a standard test of a specimen, and that should be considered. I think when you design, you will take ultimate strength or yield strength of a material to consider for designing. At that moment, at any case, under any loading, any condition of loading, the maximum principal stresses which will be generated into the component should not exceed the material's ultimate strength. That is the, I think, key point to understand here. If sigma 1, sigma 2, sigma 3 are the three principal stresses at any point of component, and sigma 1 is greater than sigma 2, sigma 2 is greater than sigma 3, then sigma 1 is the maximum principal stresses, I think, among three. That should not be go beyond the SYT or SUT, ultimate tensile strength, or yield strength in tension. So that should be by equalizing the maximum principal stress, we can have the dimension of the component. So sigma 1 should be equal to SYT or sigma 1 will be equal to SUT. The dimension of the component determined by the general factor of safety. When you will use the factor of safety, then sigma 1 should not be greater than, or sigma 1 should be less than or equal to SYT upon FOS or SUT upon FOS, or sigma 1 in case of compression. It is this is written for the compression situation, means yield strength in compression and ultimate strength in compression. The, I think, symbol stands for this. So in this way we can have some idea about it. It means maximum principal stress should be less than SYT upon FOS. These equations can be used to find the dimension of the component in case of brittle material. Let's see the region of safety. When we will draw the region of safety into dimensional system of stresses, then we will have a, I think, this picture you can see, and this picture is generally for SYT. When SYT is equal to SYC, means yield strength in tension is equal to yield strength in compression, then this kind of I think square we will have. Otherwise, in many cases it has been seen SYC is very large, very large to SYT. At that situation, in this situation, the figure will be, I think, in compression side it will be larger than the tension side, means at this side it will be small, and at the negative side, means stress side, it will be at larger in size, so that should be, I think, should be taken care of. So again, same thing, if the combination of sigma 1 sigma 2 is within this boundary, then the component will be at safer side, and when the combination of sigma 1 sigma 2 crosses the boundary of this, then component will be at, I think, dangerous side, means component may be fail. Experiment investigation suggests that the maximum principal stress theory gives good prediction for brittle material, as already said. However, it is not recommended for the ductile material. So for the ductile material, you should not choose this one, and this is very much suitable for the brittle material. So when your component is made of brittle material, the failure criteria should be chosen as maximum principal stress theory. But when it is made by ductile material, then you should go for the either maximum shear stress theory or maximum distortion energy theory. Next slide we will see how we can select and use the theory of failure. So in first point you can see, I think all the points we have already covered, but let's see one by one. Maximum shear stress theory and distortion energy theory are used for ductile material, already I think discussed. Distortion energy theory predicts yielding precise accuracy in all four quadrants. The design calculation involved in this theory are slightly complicated as compared to those of maximum shear stress theory, but it predicts better. So that should be, I think, taken care of. Distortion energy theory predicts yielding precision accuracy in all four quadrants, and but obviously the calculation is complex. In the third point you will see the maximum shear stress theory gives the result on conservative side. On the other hand, distortion energy theory is just slightly liberal, means you may have some advantage to take less factor of safety. So in this way you can understand, if you want to be on conservation side, your factor of safety will be at larger side, but when you want to be some aggression mood in design, then you should choose distortion energy theory for ductile material. Ductile material. Distortion energy theory predicts the failure most accurately. Maximum principle theory is used for ductile material. All the points we have already covered, but this is, I think, recap for you to understand how to use the theory of failure at various situations. And this is the combined drawing of all the theories, important theories, and you can see this is the boundary of maximum distortion energy theory, and this is with the help of different color I will show you green. With the help of green I will show you the boundary of shear stress theory, maximum shear stress theory. You can see this is the boundary of maximum shear stress theory, and with blue I will show you the boundary of principal stress theory. This is principal stress theory, I think you can see. This is one. So what you can see from this picture, this drawing, for any combination of these stresses, means in case of maximum shear stress theory, you will see that all the points of maximum shear stress theory comes under the boundary of maximum distortion energy theory. It means if you are designing with the help of maximum distortion energy theory, then it covers all the points of maximum shear stress theory, and you can say beyond the maximum shear theory, it is also providing some area where your component may sustain. So in this way, in case of ductile material, it predicts better dimensions. It predicts better, I think, dimensions of the component for a particular or same loading system. So that should be considered and that should be taken care of. Thank you for, I think, patiently listening of this lecture. And after going through this lecture, I hope you all have some idea about the theory of failure. And there are three theory of failure mainly we have covered in this lecture. The first two theory of failure, theory of maximum shear stress theory and maximum distortion energy theory, are related to the design of ductile material, and the last theory, maximum principal stress theory, is most widely used in brittle material designing or calculating the dimensions of the brittle material. So after knowing this theory, you I hope you will be able to use this theory to calculate the dimension of the component under your design consideration. Thank you very much.